Here we have a picture that depicts a ramp of length L, the end raised to altitude h, and a ball rolling off of the end of the ramp with some initial velocity which we're going to call v sub 0. Now that initial velocity is going to be in the same direction as the ramp. Physics tells us, and we don't have to worry about where this comes from, but if you know a little physics, we simply set the potential energy loss of the ball here equal to the kinetic energy gain, and we're assuming that the ball starts from rest. We're also making the assumption that the ball doesn't have any angular kinetic energy. That is, it comes down here with no friction and without slipping. That's not a very good approximation. However, for the purposes of pre-calculus, you can ignore the physics of that and simply accept that the initial velocity is the square root of 2 times 980 times h, where h is a height measured in centimeters. 980 stands for the acceleration of gravity in centimeters per second squared, and the 2 comes from the physics of the situation. And we don't worry about that. Now, this initial velocity can be broken into a velocity in the x direction and a velocity in the y direction. This is a standard thing that we do in physics. You don't have to worry about why, but I'm going to tell you that the initial x velocity is going to be the x velocity. As this ball falls, it keeps moving in this direction at the same speed. It moves in this direction at an increasing speed, as we know any falling object does. As a matter of fact, it moves in this direction as if it was falling with no x velocity. So we have two motions. A falling motion here that's just like the falling motion that would happen if we dropped the object, and a constant velocity motion in the x direction. As a result, the object follows a parabolic path down to the floor. This path could be modeled by a quadratic function since it's parabolic. We're not going to do that right now, but we could make that model. Now we're going to use a little proportionality. One thing you'll find about this problem is that it pulls in almost everything that we've learned. Well, we won't say almost everything. There are no exponential functions, no logarithms. But it pulls in a lot of the stuff that we've learned and shows you how these ideas all work together. Now, there's a proportionality up here of the sides of the triangle that's formed by the ramp, the table, and this imaginary line dropping from the end of the ramp down to the table. Okay, and that triangle, by the Pythagorean theorem, is going to have side L here, H here, and the square root of L squared minus H squared down here. If we do a simple proportionality, and I'm not going to go through the details of that right now, we see though that we have the same proportionality here between the velocity vector v0 and v0x. If we draw a little triangle here, we see that v0x is to v0 as h is to L. No, I'm sorry, as this side is to L. I'm looking at this thing from above and I just confused myself. In any case, that is the proportionality. And that proportionality is just this side divided by this side. So if we multiply the initial velocity by the ratio of these two sides, square root of L squared minus H squared over L, we bring the L inside the square root and call it L squared, we get an expression for the x initial velocity. And down here, the proportionality of the y initial velocity to the initial velocity is h over L. So we simply multiply the initial velocity by h over L. Now we know, if we look up just a little bit, we see that we're letting x stand for the distance that the ball travels from a straight drop to wherever it lands. See the dotted line representing the actual path of the ball here. Okay? Now, this distance x depends on two things. It depends on the initial x velocity, how fast the ball is moving in this direction, and how long it takes the ball to fall. If we multiply the initial x velocity by how long it takes to fall, we're going to get the x distance. Because, of course, when we multiply velocity by the time we're going to get the distance. 60 miles an hour times 3 hours is 180 miles. Exact same thing. Velocity times time gives you the distance. Now remember that the x velocity isn't changing, so we're just going to use the initial x velocity times the time. That's going to give us the distance. And we're going to want to get an expression for the distance in terms of the height that we raised the ramp. Now, the table is 96 centimeters high. The y velocity is therefore modeled by this function here. And this is similar to some examples that you've seen. But this is simply a quadratic function that allows us to determine the time it takes for the ball to fall. So if we know the initial y velocity, which of course is given by an expression here, we can solve for delta t, and we can obtain an expression then for delta t in terms of all this stuff, which really means in terms of h and l, and then we can get x as a function of the height to which we raise the left end of the ramp. Now we're going to assume that L is the same every time we roll the ball down the ramp, so that's just going to be a constant number, and h now is the only thing that's varying. So we want to see how x is a function of the height to which we raise the end of the ramp.